thank you, and thank you for the organizers to giving me the opportunity to present my work here. So this is work. This is based on work with David Kosshauer, and yeah, it's we're looking at techniques for the computation of rational terms of two-loop amplitudes. So just as a very brief motivation for the things we are doing. So first of all, why are we looking at two loops? Of course, two-loop amplitudes are required for theory predictions at next leading order, which promise us accuracies of the order of just a few percent. So they are essential for high precision collider phenomenology. Next, we are specializing to amplitudes of all-plus holistic configuration. And the reason for that is that they just have a very simple structure, and they tend to be the easiest after n equals 4 super Young-Mills amplitudes. Additionally, they're the easiest amplitudes that contain rational terms, which we are of course focusing on. And so that makes them excellent testing ground for developing new techniques that could then be applied to more complicated QCD amplitudes later on. Why rational terms specifically? First of all, they are a little bit more complicated, of course, since they are not constructible in 4 dimensions. So there are additional techniques involved. And in fact, for the all-plus, they actually present the last missing piece for the all-n understanding of this two-loop amplitude. Okay, so let me just review very quickly some facts about two-loop amplitudes. So generically, they can be decomposed in the following way. So where generic amplitude can be built up from a piece made up of the tree amplitude times a two-loop structure, the one-loop amplitude times a one-loop structure, and then some finite contributions, finite being here with respect to dimensional regularization, of course. And these can then be further split into finite polylogarithmic terms and finite rational terms. And the first evidence of simplicity in the all-plus case is the vanishing of the first term here, since the tree amplitude vanishes. Yeah. So the feature that is very striking about the all-plus amplitude is that one can gain a lot of ground with a nested loop approach. So what I mean by that is taking, for example, taking the decomposition of the previous slide for these two pieces here. So this is the diversion piece and the polylogarithmic finite piece. It was shown that, or it's well known for a while, that these can be computed just through one loop computation, where one of the loops is contained in, or where one of the vertices is a one loop amplitude, or specifically the all-plus one loop amplitude. And so this allowed the derivation of all-in expressions for these specific contributions. The obvious question then is, of course, to see whether something similar could be done for the rational terms. And here we have, so the all-plus amplitude has been studied very carefully in the past, and so we have lots of results available to test against. Specifically, there are results available for 4, 5, 6, and 7 gluons. Now, as I mentioned before, the rational terms are not constructible in 4 dimensions. So what typically is used is d-dimensional unitarity, where in which case the rational contributions can be obtained from unitarity cuts in d dimensions. And so we are using an embedding in 6 dimensions so that we don't have to work in non-integer dimensions. And additionally, we're taking a dimensional reconstruction approach where the amplitude, or the ds dependence, ds being the spin dimension, the ds dependence of the amplitude can be made obvious. Specifically, any two-loop amplitude can be written as a quadratic polynomial in ds. And so in this case, we are focusing on 6 dimensions. And so we are writing the amplitude as the polynomial in ds minus 6. And it turns out then that the coefficients of this polynomial are the 6-dimensional amplitude with 2 gluons running in a loop, The coefficient of ds minus 6 is the amplitude, 6-dimensional amplitude with one scalar and one gluon loop, and the ds minus 6 squared is is the amplitude of with two scalar loops. Now, one very interesting fact about the all-plus amplitude is that there is additionally a conjecture for the all-plus at leading color, given in these papers here, which states that the finite part of this amplitude can be written as a polynomial in ds minus 2, and where the coefficient of ds minus 2 is purely polylogarithmic, and the coefficient of the ds minus 2 squared piece is purely rational. And essentially, this means that this first piece makes up the finite polylogarithms, and the second piece makes up the finite rational contributions. And now the two constructions, of course, have to be the same. And we know that since ds squared is the leading coefficient, we see that there must be a connection between the rational pieces of the all-plus and the rational pieces of these 6-dimensional amplitudes with two scalar loops. And so that means that it is actually sufficient to compute just the rational pieces of these amplitudes here to get information about the rational terms of the all-plus. So why does that really make things simpler? So the thing about these two scalar amplitudes is that these scalars have different flavors. And in particular, there are no, there's sort of a flavor conservation, such that the only contributions that actually matter for this amplitude are one loop square topologies, where one scalar is running in one loop, the other scalar is running in the other loop, and there are no, these do not mix through propagators, for example, these two loops, through shared propagators. And so that means that with a conjecture, I mentioned in the last slide, to get the rational pieces at two loops for the all-plus, it is sufficient to, in this picture here, always compute one loop, the rational pieces of one loop first, multiply them with the trees of the second loop, and then again perform a one loop rational term computation. So this is this kind of nested approach again that we were looking for. Right. So what kind of ingredients are required for this? So just taking an arbitrary, one loop square topology, we first of all need the tree amplitudes in the corners, which are just tree amplitudes between a scalar pair and an arbitrary number of gluons. And so for these very compact expressions are known, so these do not really pose a problem. The central vertices where the two loops meet are, as far as we know, not really available in the literature, since there's a particular contact term, but they're easily computable via BCFW. But then the rest of the technology is completely one loop. So the loop momenta for the boxes, triangles, and bubbles are very efficient, very convenient parameterizations are known. The coefficients for boxes, triangles, and bubbles I'm computing via Mathematica, via serial expansion Mathematica. For triangles and bubbles, there are additional parameter integrals required, but those are also known, since again, this is all just one loop technology. And the same goes for the integrals. So in this case, we have boxes, triangles, and bubbles, but again, these are known in the literature. So there's nothing really, we only ever really need one loop technology to compute these two loop contributions. To verify that this actually works, we did some numeric checks. First of all, this entire computational scheme is automated in Mathematica. And so that gives us a lot of freedom about what kind of kinematics we can use. For one, we can use, of course, rational kinematics, so that we actually can compare exact results. And this using the software, we were able to verify this kind of nested construction for 4, 5, 6, and 7 gluon amplitudes, essentially for all the cases where previous results exist. But the freedom to choose kinematics, or the fact that this is all implemented in Mathematica, also allows us to use parameterized kinematics to obtain analytical results. And in particular, we are using parameterized momentum twisters, which we have used to rederive compact 4 and 5 gluing expressions this way. Okay, so all of this was at leading color so far. But the question, one interesting question, is to see whether this can be extended to subleading contributions in color. And just as a review of the, I just want to show here the color decomposition of two-loop amplitudes. And this is the generic case. And so essentially there are 4 contributions. For one, there is the leading color piece, which I've been talking about so far, which is just a single trace and 2 powers of NC. And then there's a double trace piece with a single power of NC, a triple trace piece, and a single trace without a power of NC. And so to extend this kind of one loop squared construction to non-planar case, we can identify these traces in the following way. Specifically, the outside of this kind of these one loop topologies represent the first trace, and then the other 2 traces are essentially the insides of the other 2 loops. What I mean here with inside and outside of the loop is this is with respect to the color ordering at each of the 3 vertices at the corners. And so if you were actually dressing these 3 amplitudes in the corners with the appropriate trace structures and did the color algebra, you would get exactly this kind of association to the traces. So in practice, this has the following form. So for example, taking the 5-point double trace piece, we would have contributions like this here. So for example, here 3, 4, 5 is on the trace outside and 1, 2 is on the inside. And summing over all the possible ways to assign, to distribute these momenta, that is consistent with the trace structure. And then summing over cyclic permutations, we get exactly the rational piece of the subleading partial amplitude, subleading color partial amplitude. And then the same thing also works, for example, for the double trace pieces of the 6-point, and also the triple trace pieces, triple trace piece of the 6-point as well. So again, here the one loop square topologies are sufficient to get these rational contributions. And this was verified. We verified this numerically against known results, especially at 5 and 6 point. Okay, so far this has all been about Yang-Mills. Now, of course, this meeting is called UCD meets gravity, so there must be some gravity somewhere. And this is something that we're also still working on at the moment. Specifically the application of this construction to the Graviton All-Plus amplitudes. The reason why this even would make sense to look at is that for amplitudes of positivistic gravitons, this kind of nested loop picture already has been shown to work in cases. What I mean by that is once we look again at this kind of decomposition of the graviton amplitude now, for the divergent and polylogarithmic finite pieces, it was shown that again this kind of one loop construction with a one loop vertex is sufficient to compute these pieces. And this was used for the 4 and 5 graviton amplitudes to compute these two pieces here. And so then, of course, the natural extension would be since we see that there is a method based on these 2 scalar amplitudes, is whether we can kind of transfer that also to the gravity case. And here, unfortunately, there aren't as many results available to check against, but fortunately, at least for the 4 graviton amplitude, there's a result available from numerical unitarity, which was published earlier this year. So assuming that this kind of construction works, what would be the ingredients in this case? So again, taking an arbitrary one loop square topology. There are, of course, the the three amplitudes with a single scalar pair and a number of gravitons. And these are just obtainable from Young-Mills amplitudes via KLT relations. And this has been used for the computation, for example, for the computation of one-loop amplitudes as well in the past. The thing that is less clear is what exactly the form of this central vertex would have to be. So just taking, for example, the case where there are only the four scalars, one idea would be, for example, to use KLT relation to obtain this amplitude from Young-Mills. But already there one has to deal with the fact that by using KLT relations, there's not only a graviton exchange inside this amplitude, but also, for example, the dilaton exchange, which would have to be cancelled out. And then there's also the problem that it is not clear what the contact term for these four scalars is. But so assuming that that can be figured out, just adding additional gravitons should not be a problem simply by using BCFW recursion relations. But then the rest of the technology should again be just one loop. So the loop momenta are again just the same way as in Young-Mills. There are no more coefficients due to the different power counting in gravity, of course. And there are also additional integrals in the loop momentum parameters required for the triangle and bubble integrals, for the triangles and bubbles. But these are either already known or I was able to derive them essentially in the same fashion. And then, of course, there are also additional integrals required, but these can easily be computed via dimension shift identity, via the dimension shift identities. So technologically, the only real issue here should be in this construction should be the central vertex where the two loops meet. Yeah, so this is still a work in progress. And we are not entirely sure yet what exactly the right construction is in this case. Okay, so then let me just conclude. So for cut constructible parts of the two-loop all-plus amplitudes, it is well known that loops can be kind of nested and evaluated one by one to obtain to easily obtain results. For the rational terms, this kind of nested loop picture is also applicable and also simplifies the computation of these rational terms. And particularly, there exists this connection to the rational terms of the two scalar amplitudes, which can be evaluated one by one. And we were able to show that this does not only hold for planar partial amplitudes, but also for non-planar partial amplitudes, i.e. subleading contributions. And then for all-plus graviton amplitudes, this is still a work in progress, but the similarity in the computational approach to Young-Mills makes it at least likely that some form of this procedure seen in the Young-Mills case should also transfer over to this gravity case. Okay, thank you.
That's all. Thanks, Sebastian. And we have a question from Julio.
Hi, Sebastian. Thanks for a very nice talk. So I just wanted to point out to you that there's a kind of stepping stone between Young-Mills and pure gravity, which probably would be very simple for applying your technology, which is n = 4 supergravity. Mm-hmm. So actually with David, we wrote the cut constructible. I think it's everything except for these rational terms that you're trying to determine. And we did a calculation at 4 points and they were not there. And in a sense, it's simpler than gravity because it has Young-Mills power counting. And it's also a little bit simpler than Young-Mills because supersymmetry buys you that you don't have certain classes of diagrams. So it should be nice to see if your techniques can apply to that case and to see what the result was, because all these rational terms they were very constrained by collinear limits and self limits. They had to vanish in all collinear and self limits. So we thought that they might be absent, but we couldn't tell for sure. And it seems
Okay.
that now you're set up to do this calculation. So
Okay. Yeah, that's a good hint. Thank you.
Question from Gustav.
Yeah, I guess this is kind of related to what Julio was just saying. One of the most interesting things about the All-Plus is this connection that it seems to have to n equals 4 super Young mills. And actually, I noticed there was a paper on this by Ruth Brito and a couple of others just a few days ago. I mean, I wonder if you have any thoughts on how this continues at 2 loops, because I think it is believed that this connection to n equals 4 continues there.
Yeah, so I really haven't looked into that. I mean, I do not exactly remember the reference, but I think that was, from what I read, there was like this this connection between n equals 4 and self-dual Young mills was kind of just applicable really at 1 loop, and yeah. So to be honest, we haven't really looked at that, but yeah.
Well, I mean, the connection sort of extends at the integrand level. It's something that we looked at years ago. I was just wondering if anyone had followed up on this, but it's just a matter of curiosity for me.
Yeah, no, sorry.
All right. Question from Zvi.
Yeah, so that formula you have on the screen right now, it's reminiscent of the supersymmetry word identities. I mean, they're harder to use at 2 loops, but have you thought about, just understanding the structure of these rational pieces? I mean, just the fact like they're related to the 1 loop squared, those double, anyway, those products of 1 loops. I mean, that's probably something I assume that could be understood by thinking about the supersymmetry word identities.
Okay, yeah, no, we haven't really looked at that. To be honest, we have not really looked at that.
There might be a paper, I have to think back what it was, where there was some analysis of supersymmetry at 2 loops that maybe might shed light on this.
Okay, yeah, I mean, it's not really a product here, of course. I mean, it's kind of, I mean, it's more.
No, I know, but it has a simple structure.
Yeah.
You think this can be derived from a supersymmetry word identity?
Hmm.
Yeah, it's not a product because the middle guy mixes stuff between the 2 loops, but still, I think that there's identity.
Yeah, so I mean that. So of course there is mixing in the central vertex, but only in proportional to like mu1 2 contributions. Other than that, there should not be really any mixing. But yeah, I mean, if you could point me to that reference.
Okay.